Hi there, my name's Dr. AJ Kumar, PhD. I'm doing a thing now where I'm just going to record every time I'm working, and it's ended up being good because I get a lot of benefits. So first of all, I get to see exactly how much work I'm doing. It's much easier if I need to reassemble some context. So you know how sometimes if you are working on a programming project, you've got like in your head the way that the project works, and then if you stop working on it for 2 months, you go back and you can't remember how anything works. If I've recorded the video of me working on it where I'm explaining it, I also automatically get rubber duck debugging, which rubber duck debugging is the idea you put a rubber duck on your desk and you explain your code to the rubber duck. Well, I get that here. I don't expect anyone to actually watch this. Anyway, I'm going to be working on a revelation right now, and I want to maybe show you how I do this. So the impetus for this was a great conversation I had a day and a half ago with QAnal, and I copied and pasted I copied and pasted it into here, and so and so I apologize for the language. This is a private conversation. I'm sure Craig would not mind me sharing this because we didn't discuss anything private. But so this will also give you some hint of where I'm going with the OPHDBD. Anyway, yeah, it's easy to reassemble context. I also get to see exactly how much work I've done. So how long did I spend working? Well, I record all my work. I can go look at the timestamps. Oh, I only worked for 2 hours yesterday. I also feel like if I'm publishing it, I feel the need to work more. So anyway, I have the username Darth Founder. So yesterday at 6:40 a.m., which he's in Japan, I'm in India, so there's like a 9-hour time difference. Anyway, I've realized a few things. Number one, this was me telling, Craig is a very talented programmer. He introduced me to Erlang, and I was working on OPHDBD, and I was just rambling to him about, and we have a plan in the future, and maybe you'll get to see a little bit of the plan in this video. I've realized a few things. Number one, the web is fucking retarded. 2, web apps are a fucking retarded jogger concept. Number 3, it's much easier than I thought to build an HTTP server. 4, I can build web, here, and I'll try to highlight what I'm reading. I can build web front ends to my Erlang application super easily and in a very flexible manner. And let me blow this up even more. Okay. There we go. 5, the correct way to build a, quote, web app, unquote, is to build an Erlang application and simply have a tiny little web interface that talks to it. Fucking duh. 6, Market.place, which is a project idea we have, isn't actually that hard from a technical perspective. That's kind of what I'm leading up towards. My plan right now is to just gradually turn my personal website into Marketplace, but just for me as the user, and then expand it so other people can use it. So features I'm going to add. Web frontend for WFC, pretty much done, but I have to gut WFC so that users can't introduce arbitrary atoms into my server. Those are the last few videos in OPHDBD playlist. Was me working on this. This problem number 1. Number 2, web front ends for multiplayer games I've built. I should build the games first. Number 3, a blog with crypto paywalling for my spicier posts, basically Substack. A tipping system. Way down the line, some sort of OPSS-ish. OPSS is a much more ambitious project idea that we have. It stands for the Orange Pill Streaming Service or something like that. Orange Pill Storage System, I think. There's a GitLab. Okay. I guess I'm going to call this MISC2. Oh, wait, no, it's QAnal 2 video links. And it'll be, what was I just talking about? Oh, OPSS manifesto, if you're curious about that. Okay. Some sort of live chat and community system. None of this is actually all that hard. I thought it was really hard. This shit is almost fucking impossible if you try to use any language other than Erlang, but it's really not difficult at all with Erlang. Fucking insane. I can't believe I didn't look into this language for all these years. ZXU9, or Craig. yesterday at 7:03 a.m. Bingo! The limited amount of retardation involved in just going along with Erlang MK or Rebar 3 to get Cowboy to work is basically what Loic accepted as a basic cost of implementing exactly what your idea is about web server. Darth Founder, I think it is like QAnal where I want to do everything from scratch. Now you know my frustration. I think he was replying to the thing about how it's great with Erlang and impossible with every other language. Oh, that's another thing. I'm going to develop an analytics backend and sell it as a service. I've already picked up... Here, we'll get... Hey, if you want to do it all from scratch, just do it. The overhead of writing a web server is fairly minimal, and you can always doctor it up later or switch to another code base when you want to, because you now know how it all works. The problems become transparent. Because none of the fucking other machine learning shit can distribute properly. This is an excellent growth path for you. And if I do it in Erlang, distribution works automatically. Yeah, pretty much. OP-HTTP, this is me replying to something earlier he said about getting the web server working. I said, OP-HTTPD actually works. I did it. I made a bunch of videos charting my progress. They're all up on Rumble. When it comes to using clusters, dist-url, if you need that, I can tell you how to adapt for that later, but the basic rule is if you don't use cheats from the outset like ETS and other message state violating hacks, it is really easy to adapt for both clustering and network distribution over the WAN, Wide Area Network, I think is what that stands for. There's a moment in one of them where it works for the first time and I spend about 5 minutes in disbelief that it actually works. Fucking outstanding, good job, I'll watch this weekend. And then he replying to, I think this was a reply to me saying, there's a moment where I can't believe it works. And then me saying, it's like 14 hours of video, meaning I don't expect anyone to actually watch it. Yeah, I made the videos for me, I don't expect anyone to watch them. Same with the reading videos. It's a lot easier to reassemble the context if I stop working on the project for 4 months. If there's a video, I can go watch about it. And also, if I make videos, I feel the need to work on it every day. Yeah. By the way, if you start getting into relational data theory... I know relational data theory, you idiot. I'm a mathematician. It's called category theory in mathematics, but it's the exact same fucking idea. Anyway, relational data theory and databases and whatnot, you will eventually have the same experience with Postgres that you've had with Erlang. The one exception being that you'll be using SQL instead of RuQ, because I've not had any reason to push it forward, which is gay, but trade-offs, and you'll realize how gay SQL is. But the underlying model is excellent, and Postgres is excellent, regardless of the fact that you interact with it mostly through a retarded language. And I get to see exactly how much time I've spent working on the project. The video motivations are actually pretty cool. I should screen record me working. I think he said he was going to start doing that today, so let's see. Darth Founder, I recommend it. It will just be retarded bullshit 99% of the time, but still your descriptions of motivations really rings true. I'm going to try it starting tomorrow morning. It's 22:10 here now, and I want to get some PT in before I start working tomorrow, and I want to get up a bit early. It's 7 a.m. here, so I should go to bed. Holy shit, we've been talking for half an hour. I've been distracted today with some military comparison evaluation. Yeah, he used to be an Army SEAL. Culminating in being able to convey them in a shortish way with some videos I found about an hour ago. And yeah, that was him in a different... Anyway, I want to finish graphs in the AE GUI. LOL, you're all messed up on time. You should just move out here, then you won't have jet lag. Anyway, I want to make a general graphing library. This is me for QAnal/Narrow, which is going to be my politically correct version of QAnal. So any insight on how to do graphs and oh, that was because he was talking about doing graphs, and I was like, oh yeah, if you figure out some graphs abstractions, please tell me. Graphs, I've been thinking about that. It isn't too hard to make what I've been doing and make a library out of it. I could just add it to ZX widgets as a module. My retarded plan is to do SVGs. It's just XML, I think, or some internal representation, and then draw bitmaps with Wix pixel by pixel. That might be a good thing to do just generally, yes. I have a plan to go through a data analytics textbook and do all of the exercises in Erlang/QAnal. The opacity layer is Erlang and integer arithmetic. It's all Erlang, so it works everywhere. There's a transition point in techniques between Wix 2.9 and Wix 3.1. That is kind of annoying right now. Every system except Windows is double buffered by default, But because of fucking course, thanks Windows. Anyways, eliminating flicker requires a little magic trick until everyone gets on Wix 3.1. No magic, oh, I was talking about my thing. No magic floats, no magic linear algebra library. That's awesome. We're going to have to do from scratch a lot of very basic shit, like finding eigenvalues of matrices. We really have to figure out how to tap into the math fag community somehow. This is really significant work you're doing, IMO, and the notation is inherently easy to adapt to, and it actually compiles. That's also why I've been doing the abstract algebra playlist, mostly to bone up on the algebra side of this material. That's fine. It's even really good, actually, because we can edoc exactly what the fuck is going on, which will force math retards like me to grok the gap in terminology. Yes. I don't know how a lot, this is me, I don't know how a lot of the basic functions work, like how to compute a logarithm. And it's really, really hard. Yeah. So this is where the main thread of this conversation starts. Where the interesting part starts. It's really, really hard, and it doesn't seem like anyone actually knows how math:log actually works. I think if I've actually tried to figure this out. It's not, we're going to get into that. I think if we get the data model correct and define it in an executable language, it will suddenly make more sense as an algorithm. You don't understand how, and this is me replying, you don't understand the depth of how retarded the concept of a logarithm is. And he says, this was Otto Lovelace's whole idea about language versus notation. It is the most uncomputable CIA jogger horseshit in mathematics. That was me talking about the logarithm, haha. So what is the phantom data involved? Let's move this to the CS channel. What? Oh, I missed some context. Shit. Okay, I'm going to pause the video really quick and copy the context in. I copied and pasted error, made an error copying and pasting. 1 second. Sorry about that. I made an error copying and pasting, so I had to go fix that. Okay. So here's now in the CS channel. Let me get to a real machine. Let's start by looking at Revelation 6. Now here is the impetus for this video. Revelation 6 is this one, which is on Taylor polynomials or a drive-by introduction to complex analysis. So, introduction, so here's a quote from Craig. Post-revelation thinking is never the same, and you can't make people have revelations. You can just lead them up to the point that they are likely to have one. It was talking about my revelations there, of course. All that is needed to understand this revelation is to have convinced yourself that the derivative of x to the n is nx to the n minus 1. And so I'm going to write a revelation explaining why that is true. But let me finish this conversation and so we can get some larger context about the impetus of why this was so important. Anyway, so Revelation 6, I was pointing to that as a reference because it explains in a little bit more detail the logic of this conversation, and I will probably take this diagram, make it fancier in GIMP, and then add that to Revelation 6, or I'm not sure. Revelation 6 is just a drive-by introduction to complex analysis. Okay. Image. Okay, and then image, I wrote that as a troll, so it's not very complete. It's a drive-by introduction to the exponential function. The exponential function is defined as xp of z is the sum from k equals 0 to infinity of, I wrote it in math notation for Craig, of divide pow zk by factorial k, so in, here's Rudin's definition. It's the same thing, I just wrote it there with k instead of z. Anyway, page 16 is the definition. For f infinity of x, middle of the page, here we are, 16. Okay, here. I called it f infinity of x because I wasn't telling people it was an exponential function. Slightly deeper dive in Glowy Math 1, which is, I was reading the prologue of Rudin's Real and Complex Analysis, so that's what Glowy Math 1 is. Glowy Math is my term for analysis with limits. So non-QAnal analysis, irrational analysis, if you want to call it that, real analysis, complex. Anyway, reading a book written by that's the title of the book, trying and failing, okay, that's the, anyway, totally off topic. I should spend time making a trash talk service and backend that can preserve these conversations. They will probably be important one day, even if only to my kids. Yes. Whoa. I don't know what he was talking about. It's defined, so that image, I believe, was I screenshotted this theorem. This theorem. That was the screenshot. As I just screenshotted the statement of the theorem. So, okay, yeah. The rest of it is a proof. Wet. I said Rudin. I started gushing about Rudin. Rudin is the greatest mathematics author in history in terms of talent. There's nobody else with his exposition skill. Anyway, his books are both the best for pedagogy and also the best for reference. It's incredible. And am I recording with the right microphone? It looks like I am. Anyway, I'm using him because he will have the best possible definition. So the exponential function is defined as, say, exponential of 2 is 1 plus 2 over 1 factorial plus 2 squared over 2 factorial plus 2 cubed over 3 factorial, etc. The logarithm sorry. The logarithm is defined as the inverse of the exponential function. Okay, so right away it's defined as the inverse of a function that is fundamentally not computable. But wait, let's see part E. It says exponential is periodic with period 2 pi I. What does that mean? What this means is, which image? Here. It's this image is the one I drew and showed to him. This image, okay? This is what it means. So you pick a point P, P plus 2 pi I, P minus 2 pi I. This is the complex plane, the real axis, and the imaginary axis in their standard configuration. The exponential function is brackets periodic with period 2 pi I. That means that moving by 2 pi I doesn't change its value. Now, typically, oftentimes you will say something is periodic with respect to a group action. So you can have something that's more, you can have some set of group of symmetries. I'm going to be using the group term because I've talked about groups on my channel. You can have a group of symmetries that is much more sophisticated than just translations up and down like this. And that's, I'm talking about several branches of mathematics, Lie groups, harmonic analysis. But that's a major area of study, is studying functions that are not just periodic with respect to a simple translation. So translation means moving. So moving up by 2 pi I, the function doesn't change. If you moved the entire plane up by 2 pi I and then relabeled it, exponential function wouldn't be able to tell, basically. All right, that's a bad example, but okay. So we all know the standard hockey stick exponential curve, so I think that's number 2 here. Okay. Let me explain the interpretation of that. Okay. Sorry, you lost me at it says exponential is periodic. I don't think I follow what periodic means in this sense. But here, let me explain the hockey stick exponential curve, and then we'll circle back to periodic. Okay. Okay. So what this is you take the complex plane and you restrict the input of exponential function to the real axis. And then, well, since it's just the sum, there's this uncanny valley. I took some Mucinex before I turned on the video, and there's an uncanny valley where I still have mucus, but it's like not thick enough that I can get rid of it. Anyway, If you restrict the input of exponential to the real axis, then the output will be strictly real, i.e. have no imaginary component. So if it's a complex number that has a real... So maybe if you think about it as the exponential function going from the complex plane to the complex plane, if you pick a point along the horizontal axis, it will map to another point on the horizontal axis. And if you graph this in a normal way, assuming it's a real-to-real function, so exponential input, this is supposed to be a number sign, not pi. I'm sorry about that. And then the exponential input on the horizontal axis and the exponential output on the vertical axis, it looks like the standard hockey stick exponential curve. So, and I pointed out a couple of important values. The exponential of 0 is 1. And you can tell by looking at the formula and plugging in 1 here. Well, you're going to get 1 plus 0 to the 0 squared over 0 over 2 factorial plus 0 to the third over 3 factorial plus blah, 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 blah. Where are we? And so exponential of 0 is equal to 1. And then the exponential function has this interesting property. So where is this saying? Gives this interesting property, which is that the exponential of a times the exponential of b is the exponential of a plus b. So therefore, you have this, where did I write it? Okay. So there's two key properties that exponentials have. The exponential of a plus b is the exponential of a times the exponential of b, and as a consequence, the exponential of a times b is the exponential of a to the b. The second property implies that the exponential of x is the exponential of 1 to the x. And so a special name is given to the value of exponential 1. That math number is called Euler's number, or also called e. E is an irrational number, so no finite decimal representation of it can exist, but it is approximately equal to 2.71828182459,045. So that's the value of exponential of 1 if you believe in CIA real numbers. Okay, and then it says exponential is periodic. Okay, periodic, so think of a wave. A wave is periodic. So if you imagine cosine wave, these are the most basic examples of a periodic function. Is if you move over by 2 pi, cosine is periodic with period 2 pi. Another way to think about it is if you took this graph and moved it over by 2 pi, you wouldn't be able to tell that it was a different graph. That's maybe a better way to put it. If you took the graph and slid it left or right by 2 pi, you wouldn't be able to tell that it was a different graph. Same with the sine wave. If you slid it left or right by 2 pi, which is the period of 2 pi, of period of sine, you wouldn't be able to tell it's a different graph. That's what translation invariant means. So in other words, for every point on this x-axis, if I move left or right by 2 pi, I will get to exactly the same, I will have exactly the same height. That's what periodic means. Now, if your group of symmetries of the function is more sophisticated than just translations, then you got some really interesting things going on. And if that group of symmetries is, say, continuous, meaning, or is a differentiable manifold in addition to just being a group that is also a differentiable manifold where the group operation is itself differentiable, that's called a Lie group, and Lie theory is one of the biggest great branches of mathematics, which I think I'm going to get to after I start doing some dives into differential geometry and algebra, but we'll see. What else are we doing? So that's what periodic means in this sense. It just means the value of the function is invariant with respect. So if you do a translation of the input, so the output of the function is invariant with respect to some group of translations on the input. That's what that means. and then I say read the diagram, I explained it, so this diagram. Okay, so it also works for 4 pi I, 6 pi I. This is what periodic means, and that's a diagram. Okay. My interpretation is that 2 pi I should essentially be repeating in some way. Okay. It means translation invariant. Periodic with period x means that the output of the function is invariant with respect to a change in the input by x. So if you plus or minus by input image. Translation means move in math, by the way. So to translate means to move. Second diagram. Okay, translation invariant. It repeats the same way, but at some scale. What the fuck are you talking about, man? See, I'm a math terms retard. Oh god. I tried to scan this to make sure there wasn't anything too bad. Okay. Regardless of whether I get the gist when you explain it in George Floyd language. I'm looking at exp2. Okay. The label on the horizontal... See, I wasn't really paying attention to what he was saying. I was drawing these diagrams. The label on the horizontal axis is supposed to be exp input, real number. Sorry, my handwriting sucks. Not pi. See, I wrote pi down here. So the output of exponential ranges from 0 to infinity. Right, so if you go way to the far left over here, you eventually approach 0, and it's unbounded above as you approach to the right. Okay? Okay. And infinite processes are fake because they are not quite incomputable. Oftentimes you can prove that you can tell what it converges to. So in a way, so sine is defined as an infinite series, but we know that sine of 2 times pi is equal to, or let me double check. Yeah, we know that sine of 2 times pi is an incomputable number, but we know that, and sine is not computable, we know sine of 2 times pi is equal to 0. And you can prove that even if you can't ever compute it. It's kind of weird, but you got to know some glowy math in order for that to make sense. I will give you some concreteness about what the translation invariant thing means in a second. Okay. They are definable in faggot math. Okay, I just said that. With CIA limits and CIA reals, which before Turing seemed like a perfectly valid way to construct math. I mean, we can define infinite processes in normal computable language, but we have to accept the limitations of lazy evaluation. See, this is the problem with people like Craig, is he thinks that math is supposed to make sense, and it doesn't. Because up until basically Wildberger, Euclid was the standard for math correctness, which means some things are technically unprovable. Euclid is not... Okay, and then this is me trying to explain a point that I'm having trouble explaining. Okay, let me give you a... let me give you an example. So, of what I mean by... Okay. Euclid is not compatible with Descartes. Euclid is correct, but you can't use coordinates, basically. If you want to use coordinates to do Euclid stuff, which is trigonometry, or if you want to measure angles. If I have a copy of Euclid's Elements here. There is nowhere in there where he talks about degrees or radians or measuring an angle. He can talk about having an halving, H-A-L-F-I-N-G, having an angle, halving an angle, or bisecting an angle, or trying to trisect an angle. But he never talks about measuring an angle in terms of degrees. That's a more modern idea. And he never really talks about measuring length. He can talk about comparing lengths, but never measuring them. So, one thing that the Pythagoreans had figured out, which was the Pythagorean theorem, or as a... Oops. Okay. Okay, I want here. Okay. The consequence of the Pythagorean theorem is that if I take something, if I take a function of triangle, and I'm going to do my best to try to draw it correctly, but if I take a triangle that looks like this, so a right triangle like this with you know, they wouldn't give it they would say this length is equal to this length. And what they would do is something more like here. The way that they thought about the Pythagorean theorem is different from the way you were taught it. Okay, so they would draw a square on the side like this. And then let me pick another color. These are supposed to be squares. Yeah, maybe those aren't perfect squares, but whatever. And then I Okay. What the original idea of the Pythagorean theorem was is that the area of the yellow let me make it okay, which was the yellow area. This is the original Pythagorean theorem plus the green area is equal to the blue area. That's the original idea of the Pythagorean theorem. Okay, that's the original idea. Okay, but they knew that this length, which in our modern day language is the square root of 2, which is an irrational number. I've done a video proving that it's an irrational number, which is, I think, one of the WFC videos. I'll try to remember to link that. Try to do square root of 2 is irrational. And then I'll try to remember to link to root in RCA. Okay. So you have to invent CIA real numbers and CIA limits in order to make it work. There's a few things. Yeah. Okay. Anyway, this intuition about how some things are unprovable is called the Guideline completeness theorem. It's more that it can take an infinite number of steps in order to prove something. So I think I might have this wrong. So he proved that you can always construct a statement that it takes an infinite number of steps to prove. That's, I think, a more accurate way of stating the Guideline completeness theorem. Okay. It is remarkable that the same idea comes out of a totally different direction of approach. By the way, one of my oh my god, his fucking ridiculous, retarded physics theories. Okay. One of my reconciliations between the potentially near infinite processes, that is my view, that probability is a shape and we live in a simulation theories, is that we live in a lazily evaluated universe where probability is a shape. Okay, image. I don't know what this image is. Meaning it is all out there, but nobody's going to spend the time to explore it all and discover every combination, which always evaluates in the... What the fuck is he talking about? He tells me that he doesn't smoke weed, and then he publishes this shit. Anyway. And he's talking about entropy... Okay. Blah, blah, blah. I need to go back to Revelation 6. The derivative of x to the n is nx to the n minus 1. So that's going to be the subject of the revelation that I'm going to start working on. Is explaining why that's true. Because that's basics of PreAnal. Anyway, image. What? I need to sleep on this. That image is a brain grenade for retards like me. I think that is... God damn it. Xpfn 5. Okay, it's this image. I think I started gradually adding more and more to this image. Okay. Partly because it shouldn't, wait, that shouldn't be hard, but it is because I feel like the way that I felt when I found out that functional programming is actually easier than I thought. Now I need to think about it and sleep on it. It is a mental adjustment like the typical high school football player. Question, why is I a thing? Retardation. Holy shit, I just realized you put the kanji for economic downturn on Cannon's arm in Revelation 6, ha ha ha. I need to give this a careful read, some serious thought, and I'll get back to you about infinite versus lazy. I feel like this is one of my major blockages in grokking faggot math, actually. Sine waves are circles when I change my perspective, and that sort of weirds me out. Makes perfect sense, but weird. And I. 1 second. Fucking faggot Discord won't let me upload the next PNG. 1 second. Size, yes. Okay, that was the final image. If limited, okay, blah, blah, blah. Imager didn't work. I ended up emailing it to him. Okay. Okay, so... Okay, and so I think... Let's go through this image, because this is basically the fundamentals of complex analysis in basically a flowchart. Okay, so we just talked about in one of the previous things that if you took the exponential function and restricted its input to the real axis, to the horizontal axis in the complex plane, the output is this hockey stick graph, the standard exponential curve that everybody learns about in high school. Well, what happens if you restrict yourself to the imaginary axis? And the logic of this is in Revelation 6, but what you get is Euler's formula. So every point on this imaginary axis is I, so I is this point, times some real number theta. So I times 1 is equal to I times 2 is up here, I times 3 is way up there. God, motherfucker. I times 3 is up here, I times 4, then I times minus 1 is down here, I times 0 is right here. So that's how you get e to the I theta is the exponential function restricted to this vertical line in the complex plane. E to the I theta is cosine of theta plus I times sine of theta, and this is true by definition. Go read Revelation 6. What this means, okay, and so here I was explaining that, well, here's I, 2I, minus 2I. So you take input from here, I times theta. All of them are I times theta for some theta. Feed it into the exponential function. And then here's a side note. If a complex number z is xy in coordinate form, or x plus iy, x is called the real part and y is called the imaginary part. The output is a complex number, and so you can draw these two graphs. The real part will be the cosine graph, right? So e to the I theta is cosine theta plus I sine theta. Well, you take the real part, and that's the cosine graph. And you have theta here along the axis. So maybe you're kind of you're taking this axis and, reflecting it so that it's this axis, but same idea. Cosine theta, and then the imaginary part is the sine wave, right? Cosine theta plus I sine theta, okay? Now, you combine these two waves together, which are like perfectly out of phase. We combine the two. I made a little table of values, but the table doesn't really matter. And then I made it discrete and showed kind of that it goes around in a circle counterclockwise. But you can pause the video and look at this table if you want. If you don't believe me. But really the intuition is that, here, let's make this bigger. Parametric plot of x equals cosine, y equals sine from 0 to 2 pi t corresponds to the angle measured counterclockwise from the starting point of t equals 0. So maybe this is more clear. Okay. Let's blow this up and look at this. Okay. So this is t equals 0. This is t is equal to this is pi over 4 measured in radians. Here is pi over 2 measured in radians, which is also the value of t. 3 pi over 4 radians. Now this is pi. This angle is pi over 4, which if you look at the table, that's this point. You know, this angle is pi over 2. Let me switch to a different color. This angle is 3 pi over 4, which corresponds to this point. So it's just going around the unit circle. If you take x equals cosine, y equals sine, that just traverses the unit circle in a counterclockwise direction. It's the standard parameterization of the unit circle. And you can also get there by e to the I times theta. And that is true by definition. Okay. The image traces out a circle. That is what is meant by the exponential function as period 2 pi I. Yeah, and then he's laughing about my PNG, which I don't know if you can hear my computer. It's struggling with it, and I have a beast here. All of this is leading up to the point. So I was originally on the thread of logarithms and why logarithms are stupid. And I'm going to expand a little bit more on that right now. And I'm going to close this. I'm going to save it, actually. Oh, boy. So if we plotted this, if we plotted this as an animation, it would be a particle moving at uniform speed all around this circle. Okay? And at t equals, after 3.1415, etc., if it was moving at 1 unit length per second, after 3.1415, after pi seconds, it would be here. 3 pi over 2 seconds, it would be here. 2 pi seconds, it would be back to where it started. So that's maybe a more better idea of what periodic means. And I say that waves are shitty circles, and so you can do kind of 2 waves like this that are just out of phase. So one of them you plot its value on the x-axis and one on the y-axis. Right. Okay, and then I can close all of these actually. This will kind of go through the logic a little bit more algebraically, and I want to take that diagram I just showed you and make it a little bit nicer and turn it into an infographic and add that to Revelations 4. Anyway, so what we were talking about originally was logarithms. So, the logarithm being the inverse of the exponential. The exponential is a one-to-many function, by definition. So already, oh wait, no. Exponential is a many-to-one function because it's periodic. That was my whole point with the periodicity. So, its inverse is a one-to-many function, which is not a function. By definition, that's level 0 of the retardation. There's about 50 levels that I know of. The logarithm is technically defined on this surface. I wanted to pull that up. Let's try this. Yeah, this video. What else do I have here? Yeah, oh, here's another way to visualize. God damn it. Here's another way to visualize Euler's formula. So you go e to the I theta. So e to the I times t, and you had time moving in this direction, okay, it would trace out a circle like this. And on the horizontal axis, or on the real axis down here, it would trace out the cosine curve. So you plot t going down in this down and to the left. You get the cosine curve. That's you project onto the real, and onto the imaginary axis, you plot t against the imaginary value. You get the sine wave, right? See how these are the same? All right. And then the Riemann surface. So this is the surface on which the logarithm is defined, because you remember the exponential function has this periodicity to it. So in order to make the logarithm single valued, you have to define it on this weird surface. And that's called a Riemann surface. Okay. A lot of topology. Yeah, so this is what I was saying about kind of the group thing. A lot of topology comes from looking at the Riemann surfaces of various functions and working out their geometry. The Riemann surface is equal to the retarded fake surface you need to come up with in order for the function to be single valued. It's really interesting. Anyway, level 0 is the logarithm isn't a function. Level 1, in order to pretend it's a function, you have to pick one level of the parking garage surface and just project everything to that level. So, let me open up the paint. Fuck off. Open up the painting program again. So in order to pretend it's a surface, or you need to take that parking garage and flatten it to a plane. And then what you do typically is you make a cut. So you cut out this axis and then say the logarithm is defined everywhere that isn't green. And the green includes the origin, by the way. So the logarithm is defined everywhere that isn't green, and that way it's continuous. Because you have this problem that if you're a bug here, and let's say I move along the unit circle, okay? So I start here. Here, where is my where's my circle tool? Okay. Let me color palette. Here we are. And let me control constrains ratio / angle. Okay. Here is my unit circle. Okay. And so I'm going to just start I'm going to be a bug. All right. And I am traveling along the unit circle at unit speed. Let me switch to being yellow. God damn it. Yellow. So I'm just traveling along here at unit speed. And I'm plotting my value, plotting the value of the logarithm over here. So over here, I'm the bug and I'm making a graph. Okay. And I'm going time. And up here I'm doing the logarithm. The log, okay. I can't remember how this works actually. So I'm doing the inverse of the exponential function. So what, yeah, that's right. So what exponential do I need in order to get here? So what I'm going to do actually, so what it is that like, so here, this point, okay, log of e to the it divided by I, because log of e to the it is going to be correct. Okay. Log of e to the it by definition is just going to be it divided by I, and then I get t. So what happens is that this is just purely a line, right? It's a 45-degree line. Log of e to the it, because e to the it will give me the point on this circle, divide by I. That'll give me a straight line. But now I have this other problem where I start going around the circle. oh, cool, cool, I get it here. Let me just keep going. And suddenly, I'm back to where I started. I'm back here. But somehow, the value of the function is way up here. Is going to be 2 pi, really. The value of the function would be 2 pi. So my logarithm isn't single valued. So I have to pick the typical thing. You can just pick any line, and you have to remove it. And so in order to get around this problem, you invent the Riemann surface. This is a Riemann surface. I think every function has a Riemann surface. But I'm not an expert in complex analysis. Oof. Let's see. What else? Anyway, so that's level 1 of the retardation. So you have to pick one level of the parking garage surface, right? And then so here's the parking garage surface, and then what you have to do is just put in a boundary so you can't go across levels of the parking garage, right? You can't go up to, if you agree you're on the 3rd floor, because if you agree you're on the 3rd floor, you can't go up to the 4th floor, okay? Okay. And just project everything onto that level. Level 2. There isn't a power series for the logarithm itself. There is for log of 1 plus z. And I can't remember what that power series is. Yeah, logarithm of, it's either log of z minus 1 or logarithm of 1 minus z, something like that. Okay, log of 1 plus x. Here is the idea. So see this thing in the middle, that's called a pole, where it has no value. Or maybe it goes to infinity, something like that. Okay, what I mean when I talk about a radius of convergence. So let's just pick a function like this, and I'm just going to draw poles randomly. So here's a pole, there's a pole here. I'm going to actually use different colors. Here's a pole over here, and there's one over here. Okay. If you learned about radius of convergence in like calculus or something, this is what it means. Okay. So I'm just going to pick this point, and I want to do a power series of my function. My function has these 3 poles. Okay. What radius of convergence means is the power series will converge. Nope, I want Control Z. I want circle. Is it will converge within the radius up until the nearest pole. Okay, and so if I do it, here, I'm not going to, if I do it here, let's say, then it will converge up until it hits the nearest pole. If I go here, it will converge. If I do a power series expansion centered here, it will converge. Oh, it might be log of x minus 1, something like that. I don't remember. I can't remember it. 1 plus x. So that would be x minus minus 1. So maybe that's a, I don't know. My point is that if we take the logarithm, what we can do so if we take the logarithm, and we're just pretending that it's a real-to-real function now, so our normal everyday logarithm that you learn about in high school, okay? So here is 1, and here is 2. Okay, technically speaking, if I do a power series expansion, and maybe I'll talk about what that is at another revelation, exactly what a power series expansion is. But basically try to write out one of these big infinite polynomials centered at here. Because remember, here, let's go to Revelation 6. Okay? Let's go back up to Revelation 6. Here we are. Okay. So you see these polynomials for the exponential function that I'm graphing here? So the way I introduced this, so I just said, okay, so I explained the rules for differentiation, saying that, okay, so here's a number, I called it polynomials that almost seem to have themselves as the derivative. So f of x is 1 plus x plus 1/2 x squared. So we now recognize this as the first 6 terms in the exponential series. Okay, this is the power series of the exponential function centered at 0. Okay, so the exponential function is completely analytic, which means that the exponential function doesn't have any poles. The logarithm has the big major pole. Okay? The only value of the logarithm that's really known is that log of 1 is equal to 0, which is equivalent to e to the 0 equals 1. You do that in reverse, log of 0 equals 1. Or log of 1 is equal to 0. E to the 0 equals 1, so log of 1 is equal to 0. Okay? That's really the only kind of known with the logarithm. So you expand around 1. Here we're expanding around 0, and you see how it kind of converges a little bit and then kind of goes off. Kind of converges a little bit and then goes off. Kind of converges a little bit, and so as I add more and more terms, it converges more. Now generally, for a function that has poles, it will converge within a small radius and then not converge outside that radius. And that radius of convergence is determined by the complex distance to the nearest pole. Okay, so in particular, the logarithm, if I just plot the normal log curve, let me just do that, and I'm going to just approximate it as best I can. So this is the natural log curve. Let me pick a different color. Okay, so it goes off to minus infinity. The log of 1 is equal to 0. Kind of looks like this. Like this. This is what a log looks like. Something like that. I'm sorry. That's not a great curve, but you know what I mean. We all know what a logarithm looks like. Okay? Logarithm curve. And it certainly doesn't curve back on itself like this, but that's the best I can do right now. Okay? What was I saying? If we do our power series expansion, so if we do this properly, okay, since there's a big old, let me make it in pink for pole. There's a big giant pole right here. So when we do our power series for the logarithm, when we try to write out that polynomial, that polynomial only converges in this green circle. And don't you love that my 2 is totally where it's supposed to be? Okay. Here is 2. There we are. So my logarithm power series in the complex plane will only converge within this green circle, or really it will only converge on this interval. Sorry, I should have, let me rephrase that. It will converge on this green interval, not including 2. It does not converge at 2. Because it doesn't converge at 0, it converges over here at 2. Or it doesn't converge at 2 either. So it's this open disk. But since we're only, this graph is confusing, but hopefully what I mean is clear. So, how do you compute logarithms outside of this range? I can't really seem to find very much information on this. I guess people say, well, tables. Or you compute binary logarithm. Or there's a low-level assembly instruction that does a binary logarithm. It's like, and it'll return a float. And it's like, I want to know the right way to do this. And that was the whole impetus that started that conversation. So I wanted to do a full loop. And now, how long have I been talking? Because I know I had to pause the video. So just this video, this part of the video has been 47 minutes. But I want to get into starting a new revelation and show you how I write them. So this I'll call log stuff. Okay? Log stuff. All right. CDSRC And what number am I on? I'm on Revelations 23. CP-R Rev 22, Entropism, Rev 00023. And this is called gentle preanal. Alright. Okay. So rm.get-rf, get init. Okay, xv, okay, rm rev, xv makefile, gentle preanal. Frame.tech. Shut delete, I don't care about that. I want to start a tmux. Rev 23 PreAnal. Okay, so that is my impetus for starting to write Revelations 23, and let me just get started with it. Okay, blah blah blah. Revelations 23, a gentle introduction to PreAnal. Okay, and August, it's October. By the time, ow, my goodness, my back hurts because I haven't been exercising enough. Okay, category QAnal, PreAnal, QAnal. Difficulty, this is probably a 3 out of 5 length. I don't know what the length is going to be. Question mark. Prereqs, high school algebra. Goes with videos. Yes, the one I'm recording. Yeah, topics, QAnal. Nice. QAnal. Okay. Copyright, okay. 23, gentle preanal. Include body.tech. Okay. Chap. Oh, wait, I wanted to leave that in. Okay. And it's just going to be chapter 1, introduction. Okay, ow! Let's just... This revelation, capital, aims to explain why... Oh my god. My back hurts from being out of shape. This revelation aims to explain why the derivative of x to the n is nx to the n minus 1. Okay. And I'm going to draw a couple of diagrams to explain this, but let's just make and events frame.pf. Okay, here we are. Here we go. There's Craig. Okay. Okay, and then I'm gonna kind of think about this a little bit, because Wildberger has an interesting way of framing this in his Math Foundation series, and I'm going to try to remember to link that. Oh, here's Wildberger. I was about to watch one of his videos. I love that guy. Okay, way for, yeah, okay, I don't need that anymore. Wildberger derivative Math Foundations. Alright, 5. Okay. Let me think about this. How am I going to introduce this? So I think the first thing would be, let me just draw some pictures to show why it's true. Okay? More important to understand why something is true than to be able to prove it. Okay. Okay. The reason is, let's suppose that I have a length of x, call this x, and I'm going to call this delta. Okay? So the total thing, this is x plus delta. Now, if I do that and also make it a square, so I take x okay, that's as good as I'm going to get to a square. This is x, this is delta, and this is x. X plus delta squared is equal to x squared plus 2x delta plus delta squared. Okay. And then the coefficient attached to delta is the derivative. And I want to erase this and make delta and x. So my point is, whatever is attached to delta is the derivative, and I'm going to make that intuition a little bit more formal by talking about introducing a fake symbol called delta, which is small in the fake sense that we can perfectly algebraically introduce a symbol delta, which has the property that delta is not equal to 0, but delta squared is. So in much the same way that we introduce with the complex numbers a fake number called I that has the property that I squared is equal to -1, here we're introducing a fake number called delta, which has the property that delta squared is equal to 0. Okay? Okay, and then, should I try to draw a cube? Let me try it. Let me at least try it. Okay. I'll make it really faint. Might run out of space. Okay, I need to give myself more room. Deltas. Let's call it that. Okay. So maybe let me draw the corners first. That angle is not the same. Those really the same angle, I guess. Okay, fine. There we go. God damn it, which of those is it? Okay, you know what I'm going to do? I'm going to erase all of this. This is bothering me. Okay, so first thing I'm going to do, I'm going to draw my square that I can agree on, okay? Let me just make sure it's a square. Oh, that's pretty good. Pretty good, okay. Okay, there's my square. Okay. Oh boy. Okay. Now what I'm going to do, so I'm going to agree vertical 1, 2, 3, 4, 5, 6. Okay. Okay. 1, 2, 3, 4, 5, 6. Okay. So I'm going to go with 1, 2, 3. Should I go with 3 or 4? I think I'll go with 2. 2. Okay, and I'm just going to say that's good. 1, 2. God, those don't look the same, but oh, okay, fine. Okay. One, two. 1, 2. What the fuck? Okay. And then I'm just going to make these a lot thicker. No, that's too thick. Okay. I just noticed something. And then this is delta squared, okay? Okay, now we got to build the same type of annoying structure over here. Oh my god, we also have to build it back here. One, two. One, two. One, two. Okay. God damn it, you fucking piece of garbage program. One, two. Okay. One, two. One, two. One, two. Okay. One, two. Okay, this is not drawn well. One, two. Two. Okay. Oh my god. One, two. Okay, let me just draw some. That did not look right, so. Okay, something is wrong here with this diagram. There, that looks much better. I hate every piece of software, but I really hate this piece of software. Okay. Why is this not... Oh, god damn it. Well, Jesus Christ, that's my mistake. Is I didn't... I think I can fix this, actually. Here. It's this line that I drew that's wrong. All these green lines over here that are wrong. Okay. Oh my god. I feel like... Okay, there, that's what's wrong. Is the green lines. Okay. 1, 2. Let me just double check. 1, 2. Yeah, that's right. Okay. Okay. One, two. There's no way that those are parallel. They are. See, this is why I failed art class, is because I just have no spatial skills. Okay. One, two. Just gonna. Okay, I'm getting real sick of this. 1, 2. And if I did this right, which I definitely didn't, okay, I'm just going to do this approximately because I am sick of this. Oh. Yeah, good enough. I give up. Okay. Terrible construction down here, but I'm done. I'm done giving a shit. Oh my god. Okay. I'm not going to color right now. X plus delta cubed is equal to, where is, oh my god. Why does my back hurt so much? I have this thing called a Galton board, and I'll try to remember to link it on Amazon. It's a really nice math tool you should get. Galton board. Okay. And it will be, yeah, so this And we'll get into why this is true in the revelation. 5, 4, 3, here we are. This is going to be x cubed plus 3x squared delta. Actually, let me do this in a different color. In different colors. So x cubed plus 3 no. Okay, color that's not. Okay, I know what I'm going to do. X cubed plus 3x squared delta plus, in yellow, 3x delta squared plus, ooh, I'm running out of colors, green, delta cubed. Okay? This is a delta cubed. This is x. This is x delta squared. No. This is x squared delta. This is x squared delta. This little pipe is delta squared times x. Delta squared x. This is delta squared x. This is x squared delta. And this little piece in the back here how do I denote this? There, how about that? Son of a... That is an x squared delta. That piece in the back. And then this big piece in the middle. This is an x cubed. And I meant to color code these. So, okay, the x delta squared. So the delta squared x's. So those are the long pipes. Those are going to be yellow. This is a delta squared x. Okay, this is a giant pain in the ass, and I'm hoping it's worth it. Delta cubed. Okay, and then the x squared deltas go in pink. There's 3 of them. Okay. X squared delta and here's what I'll do is I'll then I'll put little patches on which surface I mean. I might need to, let me export this as a PNG. Okay. Let me, again. Okay, and I spent so much time making that SRC Rev 023 include images. Okay. Oh, my goodness. Oh, I need to take a break very soon. Fuck you, you piece of shit. Garbage software. Deltas.xcf. Okay. Let's call it call this delta1.png. Let's call this one delta2.png. And this one, which took fucking forever and sucks, but I'm glad I did it. Delta3.png export. Okay. Alright, and then, oh my god, my back. Quit. 4, 5, 6. Save. Quit. 4. Okay. Oh, and then Jesus Christ. Oh, Revelation GitLab. I'm going to try taking my shoes off. Maybe that'll help. examples for the cases n equals 1, 2, 3 are shown the following images. The derivative in each case, the coefficient attached to delta. And to put this fact, it's in a proper formal mathematical framework. Include images, what do I call it, delta1.png, frac d dx of x is equal to 1. Okay, that's what I will do. 2 squared is equal to 2x. 3 is 3x squared. I hope I can put math in captions. And delta 1, I didn't even look at that. CREF fig delta 1, fig delta 2, fig delta 3. God damn it. I haven't even done a git commit yet. Okay. Do I need to remove the spaces? Figs 1.2 to 1.4. Okay. Yeah, if I did this with a real program, it would be better, but my back is killing me. I'm gonna stop the video here, but this is the essence of the logic. And then what we do is we invent a fake number. Okay, let me add that. The basic logic is exactly the same as with complex numbers. With complex numbers, we take the normal rational number fractions, and add in a symbol, think atom, or a fake number. Fake number, but we will explain the formality here. Number called I, which has the property that I squared is equal to -1. in calculus, we are adding in a fake number called delta, which has the property that delta squared is equal to 0. The logic of taking the derivative is roughly finding the imaginary component of a number x plus y of a number x plus y. As we will see, PreAnal is a bit more involved and deeper than simply delta squared equals 0. In fact, what we will say, but that's the basic idea, motivating idea. Let's just double check. The basic logic is exactly the same as with complex numbers. With complex numbers, we take the normal rational numbers fractions and add in a fake number called I, which has the property that I squared is equal to -1. In PreAnal, we are adding a fake number called delta, which has the property that delta squared equals 0. The logic of taking the derivative is roughly analogous to finding the imaginary component y of a number x plus yi. As we will see, PreAnal is a bit more involved and deeper than simply delta squared equals 0, but that's the basic motivating idea. Because we get more derivatives. Because we can also, here, let me say, we can also consider systems where delta is not equal to 0 and delta squared is not equal to 0, but maybe delta third equals 0. The highest exponent of delta, where delta not equal to 0, is called the term. I have an idea. Why didn't I think of this before? This term is a macro of mine. Duh. Yeah. Where are we? Order of precision. So in our case, where we say delta, we can also, for instance, zero, the order of precision is 1. The order of precision idea will replace the CIA concept of margin of error. As we will see, in QAnal, the order of precision idea will replace the CIA concept of margin of error. Okay. I'm about to die. Let me just read it. The order of precision idea will replace the CIA concept of margin of error. Okay. I think... Alright, that's about it. If anyone knows some lower back exercises, please leave it in a comment or send me an email, or like some weights, like some... Oh my god. I think... Oh my god. I checked. I haven't like gained weight or anything. It's just... Oh my god. Anyway. I think it's from abandoning the standing desk for a couple of weeks and sitting in the chair and then suddenly trying to do the standing desk again. Anyway. I'll see you in the next video where I go over this some more. Oh, let me do the Git repository. Oh my god. Start revelations 23. Okay, and it's called gentle PreAnal. That's right. Rev 00023 gentle PreAnal. Public. Fuck you with your fucking retarded main branch. Git remote push dash UL to master. There we go. Oh, I meant to. Gentle introduction to PreAnal. Why am I making? Okay. Son of a bitch. Edit the README. 23. Again, let me just make sure. Yes. Okay. Alright. Thank you for watching. How long has this been? Hour and a half. Alright. See ya.